Hello everyone, in this presentation we are going to talk about DeepWriteSYN, online handwriting synthesis via deep short-term representations. This work has been carried out by Ruben Tolosana, Paula Delgado-Santos, Andres Perez-Uribe, Ruben Vera-Rodriguez, Julian Fierrez and Aythami Morales, members of the BITA Lab from Autonomous University of Madrid and University of Applied Sciences Western Switzerland HEIGVD. The availability of large-scale public databases and the progress of deep learning have achieved very impressive results in many different fields. For example, for the task of face recognition, databases such as VGG Face 2 are publicly available nowadays, with more than 9K subjects and 3M images. As a result, deep learning technology has been able to even outperform the human performance. However, there are still applications and scenarios in which data are scarce, achieving in general poor results. These scenarios are usually known in the literature as 0, 1, and few-shot learning. One example of these scenarios is the Mini ImageNet database, with 100 different classes but only 600 images per class. As a result, the performance achieved by deep learning is much worse due to the lack of data. As a result, different approaches have been proposed in the literature in response to the lack of data, being the synthesis of artificial data one of the main research lines followed nowadays. This is of special relevance in image-based scenarios due to the popular generative adversarial networks, for example the recent style Gone 2. And also, with the combination of transfer learning techniques to better train the deep learning models for another specific task. However, when the scenarios considered are based on time sequences, and not images, the synthesis of new data seems to be a more challenging task or at least less developed due to the high variability. In this study we focus on the synthesis of time sequences data for online handwriting applications such as signature and digit recognition. Handwriting has been largely considered along the centuries as one of the most robust approaches to authenticate a person. Its application has been extended to many different authentication scenarios such as signature, password or doodles, among many others. However, a key aspect for the success of these authentication technologies is the amount of data available for subject modeling. As a result, the performance of handwriting-based authentication systems can be critically affected under one-shot learning scenarios due to the high intra-subject variability. This aspect is exacerbated by the restrictions to acquire and share handwriting biometric information for improving the learning due to legal aspects. Therefore, the motivation of this study is to overcome the lack of existing data in online handwriting applications to improve, among others, handwriting authentication scenarios. The main contributions of our study are as follows. First, DeepWriteSYN, a novel online handwriting synthesizer based on a sequence-to-sequence variational autoencoder (VAE). One of the main advantages of the approach is that the synthesis is carried out in short time segments, being able to synthesize both given handwriting structures from unseen subjects and natural handwriting variations of given subjects. Second, an in-depth qualitative analysis of DeepWriteSYN over two different online handwriting applications related to biometric systems, synthesis of digits and synthesis of signatures, achieving very good visual results in both cases. And third, a quantitative experimental framework for online signature verification, showing the high potential of DeepWriteSYN for improving one-shot learning scenarios. We describe now the proposed online handwriting synthesis approach named DeepWriteSYN. First, there is an input handwriting structure, for example, one real online signature from a given subject, with their corresponding X and Y spatial position time sequences. These two time sequences of the handwriting structure are used as input to DeepWriteSYN. Then, we use a temporal segmentation module. This module divides the handwriting into short time segments consisting of individual or multiple concatenated strokes. After that, the short time segments are introduced in a short-term variational autoencoder. This module is responsible for introducing a certain level of variation in the short time segments, producing new synthetic segments as output. Finally, the time sequences of the complete handwriting structure are reconstructed through concatenation of the short time segments, obtaining for example a synthetic signature variation for the same subject. We describe now the details of each specific module considered in DeepWriteSYN. The temporal segmentation module is an optional and interchangeable module that divides the handwriting into short time segments consisting of individual or multiple concatenated strokes. For reproducibility reasons, we make use of a simple implementation based on the velocity profile v of the handwriting. For each handwriting structure acquired, time sequences x and y related to the screen coordinates of the handwriting are captured. The velocity profile can be calculated using this equation, where this and this represent the first-order time derivative of consecutive samples of x and y. The velocity profile is divided into 4 regions using the mean, micro, and standard deviation, sigma, of the velocity profile v. Every time the velocity profile crosses one of the 3 thresholds, a stroke is extracted from the original handwriting. This figure shows an example of the proposed segmentation. As can be seen, this method allows to extract simple strokes composed of straight lines and small curves. The short-term variational autoencoder module is based on the original SketchRNN presented in HA and EC 2018. It is important to highlight several limitations of SketchRNN when directly applied to handwriting. First, SketchRNN was proposed to generate simple drawings like the ones included here. Second, SketchRNN is not able to synthesize complex time sequences higher than circa 300 samples, which is the most typical case in handwriting applications with sampling frequencies around 100 to 200 Hz. And third, a specific neural network model should be trained for each specific class to achieve accurate results. In order to overcome these limitations, the DeepWriteSYN is based on the synthesis via short-term representations trained on datasets incorporating multiple classes. Therefore, a single model is developed, which is flexible enough to generate realistic handwriting variations of a given handwritten structure within a given population or a given subject. Regarding the details of the short-term variational autoencoder, the encoder is based on a bidirectional recurrent neural network. It takes in a time sequence as input and outputs a non-deterministic latent feature vector z. Regarding the decoder, it considers an autoregressive recurrent neural network that generates output sequences conditional on a given latent feature vector z. It is important to note the temperature parameter within the decoder, which controls the randomness of the output sequence, scaling the parameters of the GMM. Both encoder and decoder are trained end-to-end following the traditional approach of the VAE, where the loss function is presented here, being LR the reconstruction loss, LKL the Kullback-Leibler divergence loss, and WKL a weight parameter configurable during training. If this parameter is equal to 0, the model behaves like a pure autoencoder. This parameter allows us to increase the variability in the synthesis process. For the configuration of the short-term variational autoencoder, we consider the same setup suggested in SketchRNN. We describe now the qualitative analysis of the proposed approach DeepWriteSYN. The first task is to synthesize online handwriting digits from 0 to 9. DeepWriteSYN is trained from scratch using handwriting digits of the public eBioDigitDB database. This database comprises online handwriting digits from 0 to 9 acquired using 93 total subjects. Handwriting digits were captured using the finger over a Samsung Galaxy Note 10.1 device. 2 different acquisition sessions are considered with a time gap of at least 3 weeks between them. In this experimental framework, eBioDigitDB is divided into development and evaluation datasets, which comprise different subjects. The development dataset is considered in the training process, using 6,200 total samples. Finally, after training, we consider the unseen subjects included in the evaluation. This evaluation dataset comprises 1,200 total samples. We show in this slide the visual images of the real left and synthetic digits right on the evaluation dataset. 2 parameters of the short-term VAE are configured to control the variability of the generated digits. First, the temperature parameter scales the values of the GMM, controlling the randomness of the output sequence. Second, the weight parameter of the loss function controls the relation between the reconstruction loss and the Kullback-Leibler divergence loss. Analyzing the effect of the loss weight parameter for a fixed temperature parameter equal to 0, very similar results are obtained for the autoencoder approach. When the value of the loss weight parameter increases, a higher variability of the synthetic samples is observed. For example, generating samples with different geometrical aspects of the loops and with strokes longer, shorter in time. The variability observed in the synthetic strokes is even higher when we increase the values of the loss weight and temperature parameters. A combination of them could further modify the intra-subject variability of the samples. The intra-subject variability of the synthetic samples can also be observed in the corresponding time sequences, red and blue color, in comparison with the real-time sequences, black color. The second task is focused on the synthesis of online handwritten signatures, image and time sequences. This is a more challenging task as the number of classes to synthesize is practically unlimited. Each of us has a different biometric signature. Also, signatures may contain complex handwriting structures such as graphical embellishment, what makes difficult the synthesis process. In this second task, DeepWriteSYN is trained from scratch using signatures from the public DeepWriteSYN DB. For each subject, genuine signatures were acquired in multiple sessions with different time gaps between them. Also, signatures were acquired using different devices and writing inputs. Regarding the experimental framework, DeepWriteSYN DB is divided into development and evaluation datasets, which comprise different subjects. The development dataset is considered in the training process using 1084 subjects. Finally, after training, we consider the unseen subjects included in the evaluation. This evaluation dataset comprises 442 subjects. We show now the visual images of the real left and synthetic handwritten signatures right on the evaluation dataset. Like in the previous task, two parameters of the ShortTerm VAE are configured to control the variability of the generated signature. When the loss weight parameter is equal to 0, the proposed approach behaves like an autoencoder, generating very similar samples compared with the real ones, proving the ability of the model to generalize to strokes unseen during the learning stage. If we increase the loss weight parameter closer to 1, a higher variability is included in the synthetic samples. For example, generating strokes longer, shorter in time. The higher the value of the temperature is, the higher is the resulting variability in the synthesis. For example, shifting the spatial position of the strokes. The intra-subject variability of the synthetic samples can also be observed in the corresponding time sequences, red and blue color, in comparison with the real-time sequences, black color. Finally, we perform a quantitative analysis of the proposed DeepWriteSYN. The goal of this quantitative analysis is to improve online signature verification considering one-shot learning scenarios, i.e., just one enrollment signature is available per subject. We propose to use DeepWriteSYN during the development stage as a data augmentation technique for increasing the number of enrollment signatures of the subjects. We are going to use as input of DeepWriteSYN the time sequences of the real enrollment signature in order to synthesize new time sequences that simulate the intra-subject variability. The bias-secure ID dataset included in the public DeepWriteSYN DB database is considered in this experimental framework. Regarding the experimental protocol, 268 subjects are considered for the development of the online signature verification and the 132 remaining subjects for the final evaluation. Also, we focus on the most challenging imposter scenario, skilled forgeries. Forgers had access to the image and dynamics of the signatures to forge and practice the imitation as many times as they wanted. For the online signature verification system, we consider the popular approach presented by Tolosana et al., based on bidirectional recurrent neural networks with a Siamese architecture. In the first experiment, we analyze the effect of the temperature and loss weight synthesis parameters on the system performance of the online signature verification system. As can be seen in the detection error trade-off det curve on the right, the baseline is drawn with a solid blue curve. In this case, only one real enrollment signature per subject is used, simulating a traditional scenario. Experiments using the synthetic signatures created with DeepWriteSYN are drawn as dashed curves, generating from the original enrollment sample 3 more synthetic samples using different temperature and loss weight parameters. Finally, the ideal case is shown with a solid orange curve, being the case when 4 real enrollment signatures are available per subject. As a result, DeepWriteSYN outperforms the baseline results, 15.32% EER versus 19.79% EER. In particular, the best results are achieved for the loss weight values 0 and 0.25 when the temperature parameter is equal to 0. In addition, DeepWriteSYN achieves similar results compared to the ideal case of having 4 real signatures, 15.32% EER versus 13.73% EER, proving the success of DeepWriteSYN. Finally, the second experiment analyzes how the number of synthetic samples generated affected the system performance of the online signature verification system. We consider the best values achieved in the first experiment, loss weight values of 0 and 0.25 when the temperature parameter is equal to 0. In general, a system performance improvement is observed when increasing the number of synthetic samples up to 12. This improvement is especially considerable for the loss weight value 0, with a 9.36% EER when using 12 synthetic samples. This is a relative improvement of more than 50% EER compared with the baseline result 19.79% EER, proving the success of DeepWriteSYN to improve already trained deep learning systems over one-shot learning scenarios. Finally, we compare the skilled forgery results achieved with the work presented by Lai and others in AAAI 2020. In that work, the traditional sigma-log normal model was considered to generate synthetic samples to improve one-shot learning scenarios. As a result, they achieved relative improvements of around 7 to 14% EER for the scenario of using one real signature and 15 synthetic. Our DeepWriteSYN approach presented here achieves relative improvements higher than 50% EER with fewer synthetic signatures needed, below to 12. To summarize, this study has presented DeepWriteSYN, a novel online handwriting synthesizer via deep short-term representations. One of the main advantages of the approach is that the synthesis is carried out in short time segments, being able to synthesize general handwriting even from unseen subjects. We have performed an in-depth analysis of DeepWriteSYN over handwriting digits and handwritten signatures, showing good visual results. Also, we have developed a quantitative experimental framework for online signature verification, proving the high potential of DeepWriteSYN for challenging one-shot learning scenarios. Finally, if you want to know more about the topic, please take a look at these other works. Also, we are currently running a signature verification competition in the 16th International Conference on Document Analysis and Recognition. If you are interested, please join. This slide concludes our presentation. Many thanks for your time.